Assalamu alaikum, my dear students. A warm welcome to all of you again for our next reduction topics. Today we shall talk about the three important reduction reactions that are well known by their names. The first one is the Wolff-Kirshner reduction, the second is the Clemmensen reduction, and the third one is the Mozingo reduction reactions. So these three reduction reactions are well known by their name of after their researchers. So we shall first discuss the Wolff-Kirshner reduction. The first one is the Wolff-Kirshner reduction. I'm sure that in your previous classes you might have an idea for the Wolff-Kirshner reduction, but we shall learn the advanced aspects of this important reduction reactions. Now, what is this reduction reaction is about? It is it involves the conversion of carbonyl compounds into alkane. Whenever we talk about the carbonyl compounds, actually these are the aldehydes and ketones. So this reaction involves the conversion of aldehydes and ketone into alkane. Let's first take the simple example of cyclohexanone. When cyclohexanone is treated with hydrazine in in basic medium, we have to use a strong base such as the potassium hydroxide in the presence of a solvent. Normally in Wolff-Kirshner reduction we use the solvent that is ethylene glycol. So what happens that this keto group, it is reduced into methylene group. So here you see we had C double bond O, but in the product this carbon has now changed into CH2 methylene group. So keto group is reduced into methylene group. You need to remember that the reaction condition, that this reaction progresses in the basic medium in the presence of a strong base such as potassium hydroxide. You might have many other solvents, but most commonly we use the ethylene glycol. Hydrogen is the main reagent for this conversion, so you must be familiar with the reagent. For example, in your exam, if someone asks you to complete the reaction, you should remember and you should also learn the what kind of the reagent is this, and what kind of the reaction is going to happen, and which functionality will be reduced. Okay, this is a very selective reaction, and this reagent is very selective. For example, in your starting compound, if you have a carboxylic group, if you have an alkene, alkyne, or many other functionalities, then and you are going to reduce that compound, this reagent will selectively reduce the keto group. It will look into where is the ketonic group is there and where is the aldehyde group is present. So it will specifically reduce that group. For example, I'm writing here another compound to make this idea more clear for you. So instead of writing all these reagents, I will simply write WK Wolff-Kirshner reduction. So what is going to happen? How many functionalities are there? Here you can see that we have a carboxylic group, keto group, aromatic ring, but this reagent, which I have already told you that this is a very selective reagent, it will reduce only keto group. So your product will be this one. Now we'll look into the mechanism of the Wolff-Kirshner reduction reaction. Mechanism. The mechanism of the Wolff-Kirshner reduction has been studied in a greater piece of papers. In many research articles, you will see many authors have written the reviews on the mechanism of the Wolff-Kirshner reaction. So this is well understood mechanism. So what is going to happen? We are using the hydrazine in the presence of a base. What happens? This base, it abstracts this acidic hydrogen and then it attached onto this carbonyl carbon, and the this pi electron density collapses. So this pair of electron moves over the oxygen, so you get O negative, NH, NH2. Did you get my point? What happens? There's this hydroxide, it plucks this active hydrogen, then nitrogen will change into NH negative. It will attack on this carbonyl carbon, which is the electrophilic center. Then this pi electrons moves over the oxygen, and oxygen gets the negative charge. So which is going to be, water is leaving, you get this compound. This oxygen, it picks the hydrogen from the solvent and we get a neutral intermediate that is called amino alcohol. Now what happens in the next step? Can I write this NH like this? N single bond H. So what happens? This bond moves here, hydroxide ion, it leaves, and you get this species. What is the name of this compound? This carbon and double bond nitrogen, which is further attached to a amino group. This class of compound is known as hydrazone. So you will say that when hydrazine reacts with ketone, you get the hydrazone in the first step. Now what happens next? Since we are using the base, now comes the greater impact of this base. This base, potassium hydroxide, this hydroxide ion it abstracts this hydrogen. This bond moves here and this bond moves here. Carbon gets a negative charge. Nitrogen, there will be a double bond here. You will get this species. Negative charge plus water. And this carbene ion, which is very much nucleophilic, it will pluck the hydrogen from the solvent, from the media, and you will get this species. What happens next? Again, a base, another molecule of the base, hydroxide, it abstracts the hydrogen. This hydrogen is very acidic and we are using the base. Base will abstract this hydrogen and this bond moves here and this bond moves here. You get another carbene ion plus N triple bond N and water. What is this N triple bond N? This is nitrogen gas. It evolves from the system. And this carbene ion, it will get proton from the aqueous medium, and finally you will get this compound. This is cyclohexane. So in start you had C double bond O. Now the C double bond O has been reduced into C double bond CH2 in the form of methylene group. Now what is the driving force for this conversion? The conversion of carbonyl cyclohexanone into cyclohexane. The driving force is the evolution of this nitrogen gas. This is a very stable molecule, and you know that this nitrogen is very inert gas. So and this gas, it shifts the equilibrium from the reactants to the product, and the entropy of the system rapidly increases. The reaction becomes the you will say that exothermic. So this reaction progresses with a great amount of heat. So all these things suggest that this is very favorable reaction. Nitrogen, it rapidly leaves the system, shifting the equilibrium from reactants to the products. So in organic chemistry you will see that all those reactions are very favorable. They proceed with great pace. That those reactions in which the gases are formed, for example conversion of a carboxylic acid into acid chloride using thionyl chloride, you will see that the sulfur dioxide leaves the system. Similarly, in using the phosgene gas COCl2, you will see that carbon dioxide, carbon monoxide, those gases are produced during this reaction. So those reactions in which a neutral molecule, which should be very inert, when it leaves the system, it rapidly shifts the equilibrium from reactants to the product. So this is the driving force of this reaction. Should I repeat again the mechanism? I'm sure you are good students, so this is not a so complicated mechanism which needs so much time. Just you will see that in the first step the hydrazone is formed. In the next step the base abstract the active hydrogen, and the electron density moves on this carbon. It changes into carbene ion, which abstract the hydrogen from the solvents. So in this way you will get this cyclohexane. cyclic alkane. Now we'll see what is Clemmensen reduction. This is another reaction in which a carbonyl functionality such as aldehyde or ketone, they are converted into alkane. Now what are the reagent of this? What are the Clemmensen reagents? So Clemmensen used the zinc mercury amalgam in the presence of concentrated HCl. When carbonyl compounds or those compounds that contain the carbonyl functionality, they are made to react with zinc mercury amalgam in the presence of concentrated HCl. This carbonyl functionality it reduced into alkane functionality. Alkane. Here aldehyde group is changed into methyl group, which is alkyl group. And this is also a very selective reagent. It will look into where the carbonyl functionality is there. It will not disturb the rest of the functionalities or moieties. You know what is the mechanism? Actually, the mechanism of the Clemmensen reduction is still not very clear, and you will see in many books that mostly they will say that actually what they have a acid, and this zinc mercury amalgam is dissolved in the acid. Zinc it loses a pair of electron, zinc changes into zinc 2 plus, and the two electrons they are present into the system. Since we have many zinc atoms, so there will be many electrons here, and you will have a pool of electrons, a pool of zinc ions, and a pool of hydrogen ions from the, because we are using the concentrated HCl, so there will be many hydrogen ions. High activity of the hydrogen ions will be there. So this is a reagent which is known as Clemmensen reagent. Now what happens in the first step? This is a polar functional group, and in the reaction medium we have many hydrogen ions. So in the first step what happens that this oxygen it gets protonated, and carbon gets positive charge and oxygen gets negative charge. Oxygen gets the hydrogen from here. You can say that when this pair of this oxygen will get protonated using hydrogen, then this pi electron will move on to the oxygen and this carbon will get hydrogen ion. And this carbon will get positive charge. What will happen next? And these electrons, when two electrons are attacked, they are added at this carbocation, it changes into carbene ion. Now this carbon it abstract the hydrogen from the system and it will change into like this. Again this oxygen this hydroxyl group, it acts as a base, it abstracts the hydrogen, protonation occurs here, and it changes into this one. It's a better leaving group, so water leaves. When water leaves, you get a carbocation, CH2 plus, and this carbocation, now we have a pool of electrons in the reagent. When two electrons are added, it changes into carbanion, and then this carbanion will abstract the hydrogen from the system, and you will finally get alkyl group, that is methyl. So I have forgot the high OH. So in all structures I will add OH. This is not the mechanism which you will see in the books. I have searched many articles, and so far what I have learned that so far the mechanism of the Clemmensen reduction is not yet fully understood. I have made my own proposals, my own uh, theoretical studies for you, that what is this reagent about. It's actually, it has the many zinc mercury amalgam dissolved into the highly concentrated HCl. Zinc and mercury both have low ionization potential, low ionization energies values, so they easily releases the electrons. So you have actually a system which has a pool of electrons, pool of zinc ions, and also pool of hydrogen ions. So what happens in the first step, protonation of this carbonyl oxygen occurs, carbon gets positive charge, and this oxygen is changed into OH. You get this carbocation. Since you have pool of electrons, two electrons are when added to this carbocation carbon, then it changes into carbanion. This carbanion, then it will gets the protons from the aqueous system or the hydrogen from the reagent. In the same way, this course of these reactions proceeds in this way. Now we will study the third important reduction reaction, that is known as Mozingo reduction reaction. This is again, this reaction involves the conversion of carbonyl compounds such as ketone or aldehyde using dithiol. In the first step, followed by the reduction using Raney nickel. Then this keto group again changes into methylene group. R1 and R2. Here we have R1 and R2, and this R2 may be replaced with the hydrogen. So remember that Mozingo reduction reaction is also a conversion of carbonyl compounds into alkanes. This reaction involves two steps. In the first step, there is a formation of the thioketals using dithiol in the presence of Lewis acid, followed by reduction with Raney nickel. Let's look into a specific example. What is the name of this compound? This is very famous compound that is known as benzophenone. When benzophenone is made to react with propane dithiol in the presence of boron trifluoride, which acts as a Lewis acid, followed by reduction with Raney nickel, you will get diphenyl methane. You see that? Carbonyl group has been changed into methylene group. So all these three reduction reactions are very similar. They start with the carbonyl compounds, they end with an alkane. Now what is the mechanism of Mozingo reduction? Mechanism. I will replace these two phenyl groups with R1 and R2. R1, R2. Now what happens in the first step? In the first step, you are going to have thioketals. I'm sure you might have an idea of what are ketals and what are thioketals, what are acetals. If you don't have an idea, you should work on it. You should write these names on the net or search these functionalities. So we have now propane dithiol in the presence of an acid such as boron trifluoride. What happens? This oxygen, it has two lone pair of electron. It acts as a base. It donates a pair of electron to this Bf3. This boron has an empty pocket. It has unhybridized 2p-z orbital which is empty. It can accept a pair of electron. So what happens? Oxygen gets positive charge and this Bf3 it gets negative charge. Now when this pi electron density moves over here, this oxygen will have no more charge, but this carbon will get a positive charge. It will act as a strong electrophilic center, and this SH thiol group, it will attack on this carbon. You will get this one. We have 3 negative. Now what happens next? There is the migration of this hydrogen from sulfur to this oxygen. How? When this pair of electron moves over here, oxygen will get negative charge Bf3, because it acts as a catalyst. It will leave as a Bf3. There will be no negative charge over here over the boron now, and this negatively charged oxygen, it will abstract this hydrogen and you will get this compound, this neutral species, OH S SH R2. I write again the previous structure. So this is the previous structure. You will get this neutral species. What happens next again? This Bf3, it acts as a Lewis acid. Oxygen will donate a pair of electrons to this boron. Oxygen will get positive charge. Boron will get negative charge, like this. What happens next? This sulfur, it acts as a nucleophile. It attacks over here at the carbon. Why? Because this carbon is getting electropositive owing to the presence of this cationic oxygen, and then this charge moves over here. You get this species. Bf3 negative and OH, they leaves the system and you get this. Now when this OH, it it acts as a base, it will abstract this hydrogen and this sulfur will get neutralized and you will get this ketal. And this ketal, since it's a sulfur here, so this is known as a thioketal. So in the first step you get thioketal. The mechanism is very much simple. When you will practice, you will see that this is not so difficult. What happens in the first step? Oxygen acts as a base. It donates a pair of electrons to this Lewis acid, followed by the attack of this sulfur, and you will get this neutral species. In the next step again, it acts as a base. It donates a pair of electron density to this Bf3, followed by the internal attack of this sulfur to this highly electrophilic carbon, and after the abstraction of hydrogen, finally you get this thioketal. And when you get this thioketal, it is made to react with the Raney nickel. Hydrogenation takes place and you get alkane and you regenerate this dithiol. Now what is this Raney nickel? I'm sure you had this idea of this Raney nickel. Hydrogenation using the Raney nickel. Although nickel is a good catalyst for hydrogenation, but the activity of the nickel could be increased using base. Actually, Raney nickel, it's an alloy of aluminium and nickel. For example, if you have this strip of this nickel and the aluminium atoms have been sputtered over this nickel. When you add base sodium hydroxide, what happens that this aluminium which is present on the surface of the nickel, it reacts with this sodium hydroxide, and it all atoms, they leaves in the form of sodium aluminate. They leave the surface, leaving behind the empty holes scattered over the entire surface. So now you have empty holes. So it creates sponge-like structure of the nickel. So Raney nickel is also sometimes called spongy nickel. And when hydrogen is adsorbed on these holes, on these sponges, this becomes a very active hydrogenating agent. So this is known as Raney nickel. So thioketals, when they are reacted with Raney nickel in the presence of hydrogen, they are reduced into alkane. Now, what are the synthetic application of this Mozingo reaction? Synthetic applications of Mozingo reduction reaction. For example, if you have this aldehyde, benzaldehyde, and someone asks you to convert this aldehyde into this compound. Now how will you convert the benzaldehyde into 1, 2, 3 butyl benzene? How will you convert? I'm giving you the hint. First, you will make the thioketal using Mozingo reaction. You will get this thioketal. This thioketal. Now what will happen if you will use the base such as potassium hydroxide or sodium ethoxide? It will abstract this hydrogen and you will get a very stable carbene ion. It will act as a nucleophile. And for example, if in the system, if you have a propyl chloride, this carbene ion, it will act as a nucleophile, and through SN2 reactions, chloride will leave and you will get this one. One, two, three. 1, 2, 3. 3 carbons are there. And how will you remove this? You will add Raney nickel and hydrogen. Reduction will take place. Add these bonds. You will get butyl benzene and you will regenerate the dipropane dithio. You see, So in order to extend the chain of the carbon atoms, you can use this Mozingo reduction reaction. Today we have discussed the three important reduction reactions. The first one was the Wolff-Kirshner, the second one was the Clemmensen reduction, and the third one was the Mozingo reaction. Now I am leaving for you few problems to solve, and I am going to give you the hint here. If you have any difficulty while solving these problems, you can discuss with me on WhatsApp. The first reaction is very much simple. Wolff-Kirshner reagent. You have to learn what is the reagent involved in the Wolff-Kirshner reduction. Simply, there will be reduction of this keto group into methylene group. Here is the same. In the first step, here you have to identify what will be the two products. In the first step, you have the Friedel-Crafts acylation, where acylation could occur, on whether this group is ortho-para-directing or the meta-directing, and which one will be the major product. If you have two products, that will, and then you will have to perform the Clemmensen reduction. Here again, Friedel-Crafts acylation will take place, followed by Clemmensen reduction. Here you will have to identify the functionalities that are going to be reduced, and here you see that keto group is present, it will be reduced. Here you have formyl group, it will be reduced into what? Here you have two functionalities, because I have told you that this is a very selective reagent. One of these two functionalities will get reduced. Which of them? Now these are two important conversions. You just need to write the mechanism, how this conversion could take place. And here you are going to have two products. Why these two products are possible? You have to give the reasons. Think over it, you will find the answer. In here you had 5-member ring, pyrrolidine, but in the final product you have piperidine. So ring expansion has occurred. What could be the possible mechanism? Try to draw the structures, solve them. I will definitely help you, and I think the rest of these three are very simple. You can easily solve them. So thank you so much, dear student. Allah Hafiz.